Well, hello, and thank you for joining us today at this presentation, at this webinar in the series of the IPERION Heritage Science Project and of the European Research Infrastructure for Heritage Science webinar series, showcasing successful projects carried out in the frame of the European infrastructure. This particular project will be given by Dr. Teresa Palomar, but before I introduce her to everyone, let me just say that the presentation is recorded and will be available on YouTube later, and invite everyone to please pose your questions in the Q&A function at the bottom of your screen. Dr. Teresa Palomar works at the Spanish National Research Council, in particular at the Spanish Center Foundation of Glass, and the research unit Vicarte. This is the Glass and Ceramic for the Arts group in Portugal, where she is currently an assistant researcher. Her scientific career has been focusing on the archaeometry and conservation of inorganic heritage materials, especially glass. In 2018, she received a special mention in the Young Researcher on Conservation Science Award, organized by the Spanish group of the International Institute for Conservation of Historic and Artistic Works. Dr. Palomar's presentation is going to focus on the Real Fábrica de Cristales de San Ildefonso, so that's the Spanish Royal Glass Factory, which has been producing high-quality glass objects for more than 300 years. Although the glass from La Granja is renowned due to its high quality, there are only occasional reports involving material characterization, which is also why her project aimed to carry out a comprehensive study of the historical evolution of glass objects produced at La Granja. This was a Molab project carried out by the IPERION Heritage Science Project. Dr. Palomar, I now invite you to start your presentation. Thank you very much.
Thank you very much for the presentation. I want to present the project entitled Historical Evolution of High-Quality Glass Pieces from the Spanish Royal Glass Factory. I'm going to begin with what is the Spanish Royal Glass Factory. You know, it's one of the most important factories in Spain. It has been producing glass during 3 centuries, and it's one of the factories in Europe that still remain its function. It is still produce glass with as in the origin in the same building. It is famous for the glassware and tableware, also for the chandeliers and the mirrors. It is said that the mirrors produced in La Granja factory was the largest in Europe in that in modern age. The Spanish Royal Glass Factory of San Ildefonso is placed in the city of San Ildefonso. It's in the north area of Madrid, in Castilla y León. It is placed in a biosphere reserve that it's called Real Sitio de San Ildefonso El Espinal. It is important because to produce glass, we need 2 basic things. The first one is to have a sand quarry of high quality near the factory, to have the raw material, but also to have access to a forest because it will be used as an energy source for the furnaces. In this case, La Granja has a lot of forests of pine wood in the nearby, so the energy was guaranteed. The history, the first furnace of the glass factory was built in 1727, where the glassmakers Ventura Cid and Carlos Sack built this one furnace in a small factory. However, some years later, the king Philip the fifth, Felipe V, the first of the Bourbon dynasty, put the factory under royal protection due to the high quality of the pieces produced in that factory. This is why, since then, it is called the Royal Glass Factory. During the middle of the 18th century, the glass factory began and has, due to the inversion of the royal crown, and was divided in 3 different factories inside the Royal Glass Factory. That is the Fábrica de Planos, or factory from Spanish glassmakers, Fábrica de Labrados, or factory of French glassmakers, and Fábrica de Entrefinos, or factory of German glassmakers. All of them made glass pieces for the Royal Glass Factory, but they had different chemical composition and different morphologies in the pieces. In addition, they had workshop for cutting, engraving, enameling, or gilding, that is decoration of these pieces. At the end of the 18th century, the King Carlos III, or Charles III, ordered to build a new factory out of the royal site due to the fires produced in the city. This factory, as you can see in the image, it's placed near the wall of the city, but out of it to protect the people of the fires. This is the building that is still in operation in La Granja, and it is still blow glass. Regarding the historical context, we have to go to the middle of 18th century, where the factory began to be famous and has recognition, national recognition. This is during all this history, there are different kings, one queen, also the First Republic, also, and during all this time, the factory produced different objects and pieces. The factory only stopped the production during the Napoleonic Wars during 5 years. In this time, the factory stopped and then recovered again the production. It is obvious that during this time, the morphology of the pieces changed according to the fashion of society. No, we began with simple pieces and then began to be decorated with enamel and gilding and painted. It is obvious that during this time, the international recognition put the focus on them, and several pieces were preserved in the most important museums for glass, such as the Carnegie Museum of Glass, the Metropolitan Collection, the British Museum, or the Victoria and Albert. However, it is absurd that there is only one study about the chemical composition of one object produced in La Granja. So it is obvious that we need information to know the evolution of this production of the factory. So this is the basis of this project. But it took a lot of years to move this, because it is complicated to analyze glass. There are difficulties, such as it's a transparent material. That means that we can have some problems to make microscopy or laser techniques because we cannot see in some cases the focus. If we can focus the surface, we have to focus or alteration or deposition or decoration. It is also an amorphous material. That means that we cannot do XRD diffraction, because we are going to have a very broad and big band that it is not possible to be analyzed. Even if we analyze the deposits or the products put on the surface, we will have this band, and we can hiding the peaks of the crystalline pieces, the crystalline products. This amorphous material also affects to Raman and FTIR because it can create broadbands instead of straight peaks. So it can be complicated to analyze them. It is also a problem with the chemical composition. We have to think that the glass can, one object can have elements from lighter elements of the periodic table, such as boron, that has an atomic number of 5, with elements very heavy, such as lead, that has an atomic number 82. This affects too much the analysis because, for example, in XRF, in fluorescence, the weight elements such as lead absorb the radiation and can affect the quantification of the light one. So we have to be very careful in the analysis. In the case of PG and PIXI, we have to make 2 analyses to cover all this periodic table for light and for heavy elements. This problematic, it's even worse with portable techniques such as portable XRF, where common equipments only analyze elements with atomic number higher than 13. This is aluminum. So lithium, boron, and magnesium are out of this analysis, but it is worse that sodium, that is a main element in glass, it's also out of this analysis. So it is also have to be very careful in this type of characterization. And additionally to this, we have to think that it is very difficult to analyze boron. It is normally don't consider in the chemical characterization of common glass because it has been addition intentionally during the modern time. But in this case, borax is also used in this glass production. So we have to also to think that this glass can have boron. But the techniques to analyze it are normally techniques from the laboratory and not portable. So all of this make very difficult to analyze. And additionally, you have to think we have complete objects that are very fragile. We cannot take samples. If we try to cut something or to make take any sample, we can create a crack and we can break the piece. And also, we cannot take out the pieces from the museum. So all of this make this project to begin in a very slow process. But we ask IPERION some help, and they answer us. We ask to know the chemical composition of the glass and the enamels, the identification of the chromophores, and the identification of the opacificants and non-melt particles that are embedded in some of the pieces. So we ask for PIXI, for reflection visible hyperspectral imaging and micro-Raman spectroscopy. Sadly, we couldn't make PIXI because we have some restriction with our national nuclear energy agency, but they also offer the techniques of total reflection mid near infrared and ultraviolet visible near infrared reflectance. So after a long trip, we obtained an access of 5 days in which 3 persons from Italy came from Perugia. Aldo, David, and Francesca came to analyze the pieces. As I said before, we make a selection of 30 objects from the 4 different periods to try to represent the most important pieces produced in the factory during this time, to know how the production has changed during these centuries. So they came and they analyzed the samples, well, the pieces. The pieces never go out from the lab, well, from the museum. And these are the results. In the Baroque period, the first period, we observe two different behaviors in the Raman spectra. You can see that most of the pieces identified with a gray asterisk has the maximum of the silica band at 1100. It is the most the behavior of the most common silica soda lime or potash lime glass. But we also have the one object that looks like an apple, that the maximum is moved to lower wave numbers. This object came from a chandelier. So we have to think that the chandeliers are made to be shiny. So normally these objects are made with lead glass that gives this type of bright color. No? So it has sense that this apple has a different chemical composition. We also analyzed one white bottle, and we discovered that it was made with calcium phosphate. There are crystals of calcium phosphate inside the glass matrix. This agrees with the recipes of that time. In the L'arte vitraria de Neri was translated by Meret and then by Kunkel. And in this last book appeared a recipe to create a glass that remember the porcelain. And to obtain it, it is said that it is necessary to use burn bones or burn deer antler, and these are the sources of the source of the calcium phosphate. So this agrees with that recipes. We also analyze the wood, and we detect the presence of organic bands in most of the pieces, and also calcium oxalate in some of them that we think are from degradation products. In the second period, the classicists, we observe the same behavior regarding the chemical composition. Most of the pieces has the maximum at 1100, and two glasses has the maximum at lower wave numbers. You can see that they have a similar morphology than other two pieces, but they can be made by two different factories inside the Royal Glass factory, maybe some of the French and the Germans. So this is why they can have a different chemical composition. Regarding the whites, we discovered that two of them were made with calcium phosphate crystals, as in the previous period, but these two was made with lead arsenate. The lead arsenate, it's common in the glass called girasol glass that was began to be produced in Venezia in 18th century. It's more or less this period, and we have it. We don't know if a Venetian glassmaker came to the factory. You have to check it in the factory. But it is true that after very few years, the Royal Glass factory began to produce this type of glass. We also analyze the chromophores, and we detect the most common chromophores in these objects, such as manganese, cobalt, and copper. And it is interesting that the bands appear with a small shift to higher wave numbers due to the use of lead glass in the enamels. In the third period, the empire, we also have again the same behavior with the chemical composition. The four bottles has the common silica glass, and 3 objects has the shift to lower numbers. That I think is due to the use of lead glass. This has sense in the case of the crown, that it has to be shiny, so like in chandeliers. The glass bottle has also has calcium phosphate, and the decoration of the other objects has lead arsenate. That is safer for people. In the case of chromophores, again, we have the same common chromophores such as manganese, cobalt, and copper. And also we did visible IP spectral, and we discovered that even they had different hues, they are the same enamel. So they are homogeneous in all the pieces. And yes. Finally, in the last period, at the end of the 19th century, we observed the predominance of the silica composition, but there is still one big jar that it has to show. It's not to use. No, it's one of these high quality pieces was made with what I think is lead glass. Also, the white glasses were calcium phosphates, and the chromophores were the same. Well, just to conclude, the Royal Glass Factory changed the morphology and the decoration of the pieces according to the fashion of each period, what we expect. We have discovered at least 2 different chemical compositions, but we need to confirm it, this chemical composition, and to try to identify how this evolved during these years in the factory. The colors are homogeneous, and because the chromophores are the most common, such as manganese, copper, and cobalt. And the most interesting were the white glasses. They were produced the complete objects with calcium phosphate in most of the cases, such as the notes of Kunkel in L'Arte Vitraria, and lead arsenate were predominantly used to decorate this the dark pieces, the blue bottles or the brown bottles, with we think with a recipe similar to the I.RIHS Darwin, that was a Venetian workbook. We think this is important because the lead arsenate are very potent. And this has sense that was used to decorate instead to make glass. To conclude again, I would like to say that this is the first step to understand the Royal Glass Factory production. This is the first time in which we has this study on in several objects, and we can compare it. However, we need more analysis, especially in chemical composition, to identify how the pieces or the production evolve in the factory during these years. And in addition, we need to analyze more pieces to have more statistics. For this study, we select the most iconic pieces to know to have this first approach to the production, but we need to have more statistics. So we need to open this study to other things such as mirrors, chandeliers, and other pieces in other museums. I don't want to finish without acknowledge to Vicart and to Instituto de Cerámica y Vidrio, also to the Real Fábrica de Cristales de la Granja, and of course to IPERION Heritage Science, because without them we couldn't make this study. in especial to the Consiglio Nazionale delle Ricerche, CITEC and SMART for the help. And thank you for the assistance of everybody. Thank you.
Thank you very much, Dr. Palomar, for this really, really interesting and insightful presentation. Before we conclude, I'd just like to invite everyone to join us again a month from now, when another such presentation will be given by Dr. Marta Oriola Folch from the University of Barcelona. Thank you for being with us today.